Hi, everybody. Thanks for joining the presentation today. I'm Tola Awofolu. I'm currently a data solutions engineer at VMware, and my talk today is on end-to-end machine and deep learning with Spring and MLFlow. So let's get started. We're going to be talking about the MLOps problem, common MLOps challenges. As a case study, I'm going to be focusing on a MVP version of a prototype that I built that uses real-time sentiment-based anomaly detection to analyze trends of customer satisfaction. A mouthful. And we're going to be talking about how we can address some of these MLOps challenges with Spring Cloud Dataflow and MLFlow, and other components, which we'll get into. So when we talk about the MLOps problem, first we need a working definition of what MLOps is. And what it is essentially practices that you would use to deploy your ML models in production, to deploy them, to manage them. And a lot of folks will use traditional DevOps principles to handle that, but there is a gap between DevOps and MLOps. And at the end of the day, applying traditional DevOps principles to ML workloads is tough. It's hard. It's non-trivial. And as a testament to that fact, there was a report by O'Reilly a few months earlier this year that said that only 26% of ML models ever make it to production. And depending on who you ask, that drops even lower. The Transform conference says only 13% of ML models make it to production. This is a challenge. And the question is, why is that the case? Well, the fact is that ML-oriented workloads are more dynamic and they have more dimensions to them that don't need to be accounted for with your traditional DevOps processes. One of them being that they're experimental by design. Each ML release is comprised of multiple iterations of experiments or runs, and those are required in order to optimize your model. And the way that you optimize your model is against production data. That's the context that it needs, which means that your initial ML release is necessarily going to be the baseline. You're going to need to have multiple iterations of optimization before you can really have a performant model. So that's one peculiarity about ML releases. And these runs, they need to be analyzed and tracked constantly and audited prior to releasing to production in order to make sure that they're actually optimized and performing as expected. And all of this means that you need to incorporate monitoring as an essential component of your validation process. You can no longer shift left on monitoring with MLOps or ML workloads. And the challenge is, how do you facilitate these runs, tracking these runs, especially when it's the case that you have a lot of loosely coupled services that are involved. You're going to have models that are collaborating with other models. You're going to have a lot of subtasks that are collaborating in order to effectively deliver on the training and tuning that has to happen for these models. So the question is, how do you facilitate tracking across all of these? There's also something that we'll just call drifts, skews, and lags that you need to account for. So you have this notion of data drift, where the data distribution that's feeding your model at training time is suddenly changed once it comes to deployment time. So as an example, let's use COVID. Say, with the use case we're talking about with airlines, perhaps there was a noticeable drop in the number of customers that were patronizing these airline services, but a good predictive model should be able to detect the data drift that happened to cause that. It should be able to detect that the reason for that was because of the pandemic affecting overall demand across different verticals, and it should be able to adjust accordingly. Same thing applies to something called model drift or concept drift or covariate shift, where perhaps your data distribution has remained the same, but the patterns and behaviors related to that are what has shifted. So to use a COVID example again, perhaps you see a noticeable increase in negative sentiment with your airline customers, but it could be because there's an underlying shift in the behaviors associated with the data points that are there. In other words, perhaps there are new variables that you never had to account for before that now you should account for to have a good predictive model. So perhaps maybe now something that factors into negative sentiment would be masking policy, or the way an airline handles acquiring vaccination records. Things like that now impact the model in a way that they didn't before. So now there's been model drift. And there's also something called training serving skews. And in this scenario, what you're using to train your model is entirely different from what you're using to serve it. So you might have different infrastructure. You're training in entirely different environments. You're using an entirely different tech stack. And this skew can result in issues when it comes to errors seeping in. So we want to be able to bridge that gap and eliminate as much of the skew as possible. And then lags, we've got this thing called feature lags and label lags. And labels are just target variables you're trying to predict. So in our use case, that would be the target variable would be whether or not negative sentiment is increasing or not. And that ground truth might not be readily available until maybe weeks later. Perhaps you're doing monthly collection of your data, so you don't immediately have those labels available to you during training. So there's some gaps there. And the same thing applies to features or inputs that you're feeding into the model that you're using to train your models and tune your models. That would leave some gaps in the training process. So all of this needs to be mitigated, and this makes it clear that in order for you to monitor effectively, you need to account for monitoring your models, monitoring your data, and monitoring even the pipelines that build these models. And that's more than just the apps and infrastructure that you're normally monitoring in traditional DevOps. So the question here is, how do you account for all of this? How do you appropriately detect and correct for drift and skews and lags? Another challenge is with the ability to scale on demand, and specifically that depends on the kind of model that we're training. So let's say you've got models that have to deal with large data sets that can't fit into a single node, but need to be able to scale perhaps in a clustered way. They possibly need to scale because you need more memory in order to process them, because you just got a lot more data that you need to account for. So that's a more data-centric perspective on the scalability that you may need. And in other scenarios, perhaps you just have very complex models or really large models that need a lot more compute in order to process. And in that scenario, you're going to need to go out a core in order to have more cores doing parallel crunching to perform the training that's required or the tuning that's required. So the question here is, how do you scale on demand to accommodate this? And another challenge here is just the general lifecycle management process. In general, when you're talking about release pipelines for ML workloads, you need to be able to account for not just your continuous integration, not just your continuous deployment, but also now you have to factor in continuous training, because you've got the shift, you've got the skews, you've got the lags and different things that are changing in your environment that you now need to be able to account for and adjust. And you have to do that on a continual basis. So now you're training regularly, and that needs to be an important part of your release pipelines now. And when it comes to management in general, managing machine learning workloads needs to account for more than just your code artifacts. Now you need to obviously manage your models and also the configuration that surrounds the models, the metadata that surrounds those models, and things like that need to be accounted for. And so the question is, how do you adequately handle all of that? How do you now handle lifecycle management? So here I'm going to talk about a case study that I had built as an MVP to demonstrate. The domain is on the airline industry. The problem that we're talking about is a trend detection problem, and the objective is to monitor customer posts on a message board and perform an action when there is a visible increase in posts that have negative sentiment. So this combines quite a few scenarios. You have a classification problem of being able to detect negative sentiment over time. You have an anomaly detection problem where you're trying to identify if there's new spikes in negative sentiment, and you want to be able to alert when the rate crosses a certain predefined threshold. And what we're interested in here are the peaks, not the valleys so much. And there are many reasons that one might be interested in this. Perhaps you want to get in front of your competition. You want to be able to identify growth opportunities. You might want to be able to predict customer churn. There are several reasons to be interested in something like this. So here is a quick fire overview of how you might attempt to approach the life cycle for this. The first step would be to scope and define your problem. And part of that is identifying potential candidate models they can use as a baseline. So given the nature of the data being sequential, you might want to consider time series models. These are time-stamped data points, and that you can leverage for time series models. And machine learning, there are several approaches for this. You can use a family of models called ETS, and ETS stands for error, trend, and seasonality models. And what that's basically saying in a crude way, I'll explain that that's talking about models that are able to analyze random processes, but take into account things like trend and seasonality. Say, perhaps there's an increase in negative sentiment during the holiday season, perhaps. Maybe people are just more stressed during the holidays, so people are just more negative in general, or for whatever reason, perhaps there's a higher spike in negative sentiment during that time. A good predictive model should be able to identify that the uptick in negative sentiment during that time was actually not a result of it was not actually an anomaly, but it's actually expected because of the period of time that it's in because of the holiday season. So in this case, we're using ARIMA models, which are good for detecting these trends and seasonality. And we can also do RNN models, or recurrent neural networks, which are a form of deep learning models. And those are very data intensive. Usually you don't want to do that if you don't have the scope of data that warrants it, but they're very flexible. They could find things that machine learning models sometimes can't find. So we're just going to throw that in as another candidate model, potential candidate model. As far as detecting anomalies themselves, we would use a probabilistic-based approach. There are other approaches you could use, proximity-based, you could use regression as well, but we'll use probability-based scoring. We'll just try that. We could use other approaches. Again, we're doing experimentation. And here the idea is, by the time you take out the trends we talked about and you take out the seasonality, what you're left with is just a regular normal distribution. And so you can apply your statistical tests like z-tests or t-tests or similar in order to detect anomalies. And then the question is, you need a way to see that the modeling that you're doing is actually going to perform well. So how do you do that? That's where ML metrics come in. So you might use things like regression metrics, and regression metrics are often used for regression type modeling. So in this case, you would be able to have a measure to compare your predictions to the actual. And there's tons of measures that you can use for that. And you also want to be able to monitor the trend of anomaly scores and see if it's peaking or the trend is going above what's expected. So those are things you want to track. And then also, you want to have an NLP model for sentiment analysis. And in particular, specifically, you would want something that can do an embedding. And embedding is just something that takes the raw sentences and posts and words and converts that and vectorizes that and transforms that into a numeric version that a machine learning model can understand. So that's what an embedding is. And TF-IDF is just an example of an embedding that you might use. And you feed that vectorized data to your logistic regression classifier. And in this case, what the classifier is doing is just basically identifying, is this sentiment that you've presented here, or is this post that you presented here, is it negative sentiment, or is it positive, or is it neutral? And in this case, it's a classifier. It has well-known classification metrics that are classically used to analyze the performance of whether it's giving a lot of false positives, false negatives, and so on. So there's a lot there. So the idea here is that you would actually require several things in order to implement this. Given the nature of the data, given that it is streaming data, ideally, you would want to have a streaming data source that you're able to integrate with. For several reasons, this would be continuously flowing data. It's likely that it won't have a start and stop to it. So a streaming data source would be ideal for capturing that kind of data. You want a data source that's able to honor the ordering of the outcomes, because that's necessary for time series data. We need to also be able to have to track some past history and not necessarily forget all the data as it comes in, but we want to be able to keep track of history of the data, because we know that historical data allows you to have more accurate forecasts and predictions. So all of that is something where a streaming data source checks all of those boxes. So we want to be able to seamlessly integrate with a streaming data source in order to implement this. We want to be able to use an online training approach as opposed to a batch training approach, which will allow us, instead of having to do a batch mode of training where we're training the data set from beginning to end, we're training the entire data set. This is a data set that's rapidly changing, constantly changing over time. So instead of doing that, we want to actually train the data in increments. Perhaps we'll take rolling window chunks and train against those subsets instead. And that's what online training entails. Instead of having to do a batch mode of training an entire data set at a time, we're doing increments of data. And that approach has pros and cons to it. So now we have shorter life cycles, which is a good thing. We've got the ability to train smaller data sets at a time, which is also a good thing because it allows us to have quicker feedback loops. But there's also the disadvantage that now we have more compute intensive requirements. Now we need to be able to handle rapidly and increased number of training life cycles per period. And also because it's really nearly impossible for you to have human in the loop intervention when you're doing multiple constant training iterations. Now some of the approaches or some of the processes that a human would have been injected into to handle, you're going to need to automate. And now we definitely need to do real-time tracking of these ML data metrics that we're talking about. And in terms of automation, now that we're not going to necessarily have as much human intervention, we need to be able to automate things like your deployments, your promotion of models from one stage to the next. We want to be able to enforce deployment strategies that allow us to easily roll back if it's detected that that's necessary. We want to be able to implement progressive deployment strategies like canary deployments, blue-green deployments, and those kinds of deployment strategies, because now we're doing automated deployments. So we want to be able to effectively deploy and progressively deploy and roll back when necessary. And we also want to have something that provides polyglot support. So I'm using Python for this MVP, and Python is a preferred language in the machine learning community. And the idea here is that I would like to remain Pythonic even in this architecture. So we want something that's interoperable with various languages and frameworks. And here is the end result. And this is what actually ends up being used for the MVP solution. So we've got Spring Cloud Dataflow, which is orchestrating these various tasks, these various ML tasks. We've got MLFlow, which actually handles the varying aspects of the life cycle, whether it be tracking the various metrics and the configuration data and metadata and artifacts and so forth, whether it be being able to serve the models, being able to deploy the models, transition the models, being able to store them, register them, the ability to also track the performance of the model, again with metrics, the ability to package the models in reusable packages called ML projects. So all of these things are things that MLFlow provides. And then Ray provides that distributed compute that we need for the scalability issue that we talked about. And then we've got Prometheus, which is that layer that handles actually ingesting, collecting the ML and data metrics and resource metrics we were talking about. And Prometheus has built-in integration with Spring Cloud Dataflow. So we're just going to be feeding into that. And on top of that, we'll just mention a couple of things. This is all running in Docker containers. In order to run non-Java applications in Spring Cloud Dataflow, they need to be running in Docker. And they're also all running in Kubernetes. And that gives you the advantage of being able to more easily automate some of these aspects, like the automated deployments and rollbacks and scalability and scaling on demand, I should say. So now we've scoped the problem and we need to be able to handle data ingestion. And that's where we talk about being able to integrate with data pipelines. And data pipelines, this meaning your classic ELT, TL processes that are focused on operational workloads and handling data crunching, data extraction, massaging data, enriching the data, storing the data, and loading the data into different sinks and so forth. One of the points that data scientists tend to spend a lot of time on, some estimates say up to 80% of their time is spent here. Between this and feature engineering, it takes a lot of a data scientist's time. And this is where we're actually integrating with the data pipelines that feed our ML pipeline processes. And there's some overlap with your ML pipelines, but your ML pipelines are focused on your models. They're focused on model training, they're focused on model inference, and experimentation and analytics based on those. And so the idea is it's good to keep those separate. It's okay to keep those separate, but how do we enforce that decoupling while still allowing there to be the data exchange that's required to do the training that we're talking about and the training and tuning we're talking about? So we've done the data ingestion, we've ingested the data, and now we're ready for feature engineering, which is transforming that raw data into the format that will be useful for your machine learning models. And again, this is one of those points where a data scientist spends most of their time. So it's really important to get that right. As a matter of fact, there's a rule that says that you can have a perfect model, but if you have bad quality data, then the performance is going to be bad. And on the other hand, you might have a less than perfect model, but it would perform great if it has great quality data. So it's important to get this right. And I'm not going to focus on all the nuances there, but one of the aspects that's relevant here is the ability to perform featureization at scale. You might have feature processing that requires the ability to scale beyond just one machine node. And for something like that, we need to be able to integrate and interoperate with tools that allow you to do that. And in this stack, Ray actually provides that distributed compute. You can actually have processing tools on top of that, like Modin, which is like a drop-in replacement for Pandas, which will allow you to do some of this feature processing. And there's tons of other solutions that you could use that all integrate seamlessly with Spring Cloud Dataflow. Then you've done your data ingestion, you've done your feature engineering, so now you're ready to get into your model training, and that's where you're building their model, you're training it against a training set, you're doing your cross-validation, and then you're testing it against some holdout set. And then you might also here do some hyperparameter tuning, you might do some grid search, and some other things that are really compute intensive that might fit into this stage as well. And here we basically want to have, just like with feature engineering, a scalable compute environment, because we're going to, especially since we're going to be doing a lot of retraining cycles because we're in this online mode. So we really need to have that scalable compute. And another thing we need here is the ability to have reusable training steps across different pipelines. And that will help with the training serving skew that we talked about earlier. So one of the issues was that you didn't have the same baseline that was used with your training setup or your training tech stack and your serving tech stack. They had disparate baselines that they're using. So MLFlow does provide the ability to package these models in a reusable format. It's called ML projects, and that can actually be used across different pipelines. So that's one solution there. And then we talk about model selection. And at this point, we're talking about taking the model that we just selected and trained and passed validation and so on for this cycle. We're taking that model, but we're also taking other models, perhaps from other training cycles. Perhaps we're taking, maybe we might take the Riemann model compared to the way the RNN or the LSTM or another model performed. We're basically taking all of the models and we're going to be doing evaluation across all of them. We're going to have specified thresholds for metrics that they need to scale, and whichever ones perform the best, we might transition to the next stage. Whichever ones fail to even pass the threshold, we might archive or delete. And the idea is we want to be able to do this in an automated API-driven way, and MLFlow does provide a models API that does just that. And again, you can orchestrate all of this on Spring Cloud Dataflow. Then you got this model deployment. stage. After you've actually selected a candidate model that's ready for production, you don't want to do a big bang switchover. You actually want to use an iterative approach to ease this model into production. And there are various approaches you can use for this. So for example, you might deploy this new candidate model as a shadow deployment that's running in parallel with the production model. And it's not actually doing anything. All you're doing is you're monitoring it to see how it's performing over time. And then once you observe it and you see that it's actually performing well, then you move to the next step of doing a canary kind of deployment where you're allowing routing production traffic so that a little at a time, maybe 10% reroute to that canary deployment and 20% and so on until you get to 100% when you're fully confident that the performance of this new model is where it needs to be. And at that point, you can shut off the old production model. So the idea beyond the ability to monitor this, because obviously you're going to need to be able to integrate monitoring in order to see how the performance is going. You also want to be able to automate this so you want an API driven approach for doing this. And again, you've got the MLFlow models API to help you with this. Again, running on Spring Cloud Dataflow. And so with all of this said, you have this implementation, or I have this implementation of an MVP that basically is all running Spring Cloud Dataflow. So you've got Spring Cloud Dataflow that was used to implement the data pipeline, which is actually serving as the streaming data source for the posts that come from the airline customers. So this is actually using RabbitMQ. It's using RabbitMQ streams for that. And you've also got the ML pipelines, which are also running in Spring Cloud Dataflow here. And they're all running with Python, using Python ecosystem, using stats models for the ARIMA models, using scikit-learn for the NLP models, using TensorFlow Keras for the RNN models, and all of this is Python. And then you've also got MLFlow for the ML lifecycle related aspects that we talked about. And for distributed compute, we're using Ray clusters, and you can use other approaches here too for your distributed compute. I integrated Ray here just because it's really easy to integrate. You just throw decorators on your Python functions, and then voila, you're able to integrate with these Ray clusters. That's a high level. It's basically fairly easy to integrate into Python code. And you can also throw a lot on top of Ray. So that's that with the high level implementation. And I also want to highlight a feature that Spring Cloud Dataflow provides, which is the ability to tap a stream, and what that's talking about. And when we talk about a stream in Spring Cloud Dataflow, we're just talking about a graph of tasks, but a stream oriented version of that where the different tasks are connected to each other over messaging middleware. And in this case, the binder I used was RabbitMQ, so the messaging middleware was RabbitMQ. So the idea of tapping a stream is that every stream that you create or you deploy in Spring Cloud Dataflow has an associated so-called name destination, and that's a destination that you can publish to or consume from. So in this case, you might have a RabbitMQ exchange that's automatically created for each pipeline, and you can actually publish to it or consume to it. So by just invoking this tap, we're able to basically consume from this data pipeline. And the syntax is something like what you see here, roughly. It's very simple to do. It's not a lot of wrangling in order to implement this. So this allows us to begin to have the ability to easily integrate our ML pipelines with the data pipelines. A couple of other aspects that I'll highlight here, and a lot of this is really covered in the GitHub link that will be at the end here. So we've got ML model, or I should say, Spring Cloud Dataflow allows you to implement your own custom processors, and processors would be like your operators or connectors in other frameworks. So it allows you to implement your own custom processors. And here I implemented this ML model processor. And what it does is it allows you to execute custom Python code as MLFlow projects. So it allows you to inject Python code that comes from a GitHub repo that hosts an MLFlow project or an ML project, which again is a reusable package of an ML model. It allows you to inject that into a processor that will now run as part of a data flow stream. And there are several ports that are exposed in order to facilitate this. We've got data ports, which basically are like connectors that allow you to integrate with various services on your ETL cluster or your training cluster, your tuning cluster. So it will integrate with anything from a data lake to your database, to your S3 object store, to Spark, and to Kafka topics or off-platform Rabbit queues, and so on. So those are data ports. And then you've got a control port, which is basically like the driver port that actually handles executing your processor as an MLFlow run, which is again like an instance of an experiment. And you've also got the monitoring port, which actually handles exporting the various ML metrics we were talking about to the Spring Cloud Data Flow Integrated Prometheus. And here is a sampling of how you might create a stream with that ML model. In order to activate those ports, all you would do is put in this decorator that I also implemented as part of this MVP. And what this decorator does is it allows you to actually plug the ML model into the data flow stream. So what it does is it's the one that takes the GitHub repo that has your ML project from MLFlow, and it allows you to integrate that with parameters from your processor in your Spring Cloud Data Flow stream, and it then injects those into your Python ML function. And for more on that, I've got the GitHub link here so that you can check out more about how that works. I've also got a demo that's embedded there that you can check out, and there's also this link that shows you how I incorporated the recipes for incorporating workloads like Python on Spring Cloud Data Flow. So with that said, that concludes this talk. I hope that gives you a good idea of how you might leverage Spring Cloud Data Flow for machine learning and deep learning. Thanks for listening.